And that's just a little phrase that's kind of loosely thrown around in terms of, well, what's his character kind of issue. Well, there are several named topics that we need to look at. Now, this also is an order in which you consider a molecule, and then you come out with a conclusion as to its chemistry. First thing that needs to be considered in evaluating a molecule is its electronegativity nature. Electronegativity, by definition, and we'll repeat this in a minute, is an element's attraction for an electron cloud. The more protons it has in the nucleus relative to the electron cloud, the more of attraction it has, and that will change the bond structure and strength of the bonds that are associated with a certain structure. Okay, now also electronegativity is responsible for bond polarities, which ultimately lead us to things like partial positive charges, partial negative charges, or dipole moments, and that as a result is a big issue in considering how a molecule would react at whatever site in that molecule it would be considered. An unequal distribution of electronegativity around the molecule leads to what is known as molecular polarity. These three topics are of ultimate importance when trying to evaluate the chemistry of a given structure. Now, the bigger picture of this is we're going to be short in terms of explaining the big picture. That's why I give you these two references up here, Weeks Pushing Electrons and van der Waals acid-base chemistry of the covalent bond. The second one approaches the reactivity of molecules in terms of acids and bases and the electronegativity concept. Well, the first one takes into account electron pairs and non-bonded pairs and how they move around and cause chemistry to change in molecular reactions. So if you're going to the next level, I encourage you strongly to try to get through that or take it with you as you go through the course. Now, one that's not in the little list, and I have inserted it as I've been going along one of these days, I'll put it in formally, is bond making and bond breaking. Now, a chemical bond is an electron pair, and an electron pair can break in one of two ways. It can break homolytically. In other words, one electron goes with one element and one electron goes with the other, and that produces what is known as free radical pairs. Or you'll have a bond cleavage where both electrons goes with one element while the other one is deficient in both of those electrons, and that creates what is known as a formal charge. So that would be the next one, and formal charge is a result of bond cleavage leaving behind, say, a carbon with a positive charge, a carbon with a negative charge, or any other element with a charge structure that is important in the chemistry. Need to. There, that's probably a little bit easier to read now. And formal charge has a very specific formula that you use to calculate the specific formal charge contribution of an element within a polyion, for example, and the sum of all the formal charges algebraically will give you the overall polyion net charge, and we'll do that when we get there. And finally, you consider if the molecule, some molecules have it and some of them don't, resonance. And this is a condition where the electrons are distributed over the entire molecule, or several bonds, and makes the molecule highly reactive at those resonance sites. And so you certainly want to know if a certain structure is resonating, and that would be when you try to react it with something else for whatever, you would expect the outcome to probably attach to that resonance point in the molecule. So when you start evaluating a molecule after your ABO Beck and you've drawn out your two-dimensional structure, let's say you came out with something that looked like this after your some fancy looking molecule, and you came out with this. Okay, so your job now is to go through this molecule. Let me put it up here where you can see it. Go through this molecule and say, well, what's happening here? What's this kind of reactivity here? How about this site right here? What about the OH on the ends and things like that? What will they do? Okay, and the course of the chemistry that you are trying to understand or working with this molecule as you proceed to the next level, which is, of course, what will it react with? Okay, so that's what you will do. You'll first consider, well, what's the electronegativities of the different elements, and then you'll look for bond polarities in here. You'll look for molecular polarities at certain sections. Well, what will break and what will not break very easily, and what's the formal charge at partial charges in some of these places if I break a bond, you know what, and then does this have resonance? And so by having a systematic list of things, topics to go through while you're evaluating a molecule, when you get through to the last topic, whoa, I see what the molecule can do, so you can go get another molecule, throw it in there, and you expect it to react. And that's next level. But right now we want to go through and see what a molecule will do. And that's molecular dynamics. This is electronegativity of elements. And electronegativity fundamentally is an element's attraction for electron cloud. Okay? And we've seen a little bit of this in the series versus the series of radius, of valence radius, or size of the molecule, elements. So if we look at, say, sodium, magnesium, and we keep going down the chart, we'll see a decrease in atomic radius. Okay? This is a nuclear attraction for electron cloud. If we went, say, from sodium, magnesium, then jump over to aluminum, silicon, phosphorus, sulfur and chlorine. Put chlorine in here. Like that. Now they get smaller because the nuclear attraction gets stronger for the valence electrons. Now we're primarily concerned down here in the non-metal world for electronegativity. Now when you look at a periodic table, so looking at the periodic table from left to right here, we're getting smaller radiuses. So all of the elements as we go across, you are increasing the pull. Now that increasing pull is an increasing attraction, which is increasing electronegativity. So from left to right on the periodic table, you're increasing electronegativity. So as you go across. So elements on the right side, carbon, nitrogen, oxygen, fluorine, would have in order increasing electronegativity. Carbon would have, for the most part, in what we're talking about in molecular bonding, we're just talking about carbon, nitrogen, oxygen, fluorine, silicon, phosphorus, sulfur, and those. But nitrogen has greater electronegativity than oxygen, than carbon, and oxygen has greater electronegativity than nitrogen, and fluorine has the highest, and it would be strongest attraction. So if it was bonded to something, it would suck all the bond electrons toward it. And this one, whereas carbon wouldn't. And the higher the electron density, the higher the strength. And I call it glue. The more electron you have, density you have between two nuclei, the stronger the bond, like a double bond, triple bond versus a single bond, this kind of thing. The more bonds you have, the more glue you have between nuclei. And so that's what happens as a result of electronegativity. Carbon having a low electronegativity in the sequence would not pull the charge out of the bond. Carbon bonded to hydrogen. This would be a relatively strong bond versus fluoride hydrogen, and that would be a weak bond. And that's what governs your understanding of chemistry. Well, bond making, bond breaking. Well, if I threw a carbon-hydrogen bond into a reaction, would it react? Or would I need a fluoride hydrogen? I'm just throwing that out because this one would react a lot faster. Then this is a very strong covalent bond because the carbon doesn't remove any of the bond density in here, meaning electron density, where this is real strong attraction and would build up the electronic charge around the fluoride, and this thing would carry a negative charge, and hydrogen would carry a positive charge. It'd be a dipole. But the carbon wouldn't pull anything away, and so you would have an equal pull, and you wouldn't have a dipole, any charge at all in there. And so if you don't have any charges, you're not going to have any reactivity to any extent. So the idea in molecular reactivity and molecular dynamics is opposite charges. Positives looking for negatives or negatives looking for positives. If you don't have that, you're not going to get a reaction. So the simplicity of the chemistry that you're looking for is all in this electronegativity. That's the most important word in molecular reactivity. Well, does a site have a lot of pull or not so much pull? And that ultimately defines whether or not that site on the molecule, when I talk about sites, that's a carbon site or whatever, is a reactive site or non-reactive site. Okay, now the other side of the coin real quickly is going down the chart, down this way. As you go down the chart like this, you're decreasing electronegativity, the nuclear influence on the valence side or attraction of electrons. Why? Because you're adding rings as you go down. Fluoride has 2 energy levels, 2 rings. Chlorine has 3 energy levels. So the interaction of the nucleus with the 3rd level is going to be less than that of fluorine. So the electronegativity is going to be less in terms of the nuclear effect of fluorine on the ring valence than chlorine's nuclear effect on the valence. And you get down here to iodine. We don't look at acetine that much. Iodine, it's out 1, 2, 3, 4, 5 rings out there, and you've got 4 shielding any effect or influence of the nucleus on that outer shell valence structure. So this would be very low, and if you had a hydrogen hung on there, it would ionize very quickly. It wouldn't be held on very tightly, so it would be a stronger acid. Versus a hydrogen hung onto fluoride, it wouldn't be a very strong acid because it's hard to deliver the hydrogen from it. It'd be a stronger bond because electronegativity is so much higher. And so the first term that you have to get control of mentally in understanding molecular dynamics is this word electronegativity, because it governs everything else we're about to talk about in terms of reactivity of molecules. And in working with molecular structures, the issue is going to focus primarily on your non-metals as you go through this. And so this is this region over here. You pick up videos tonight, okay? Okay. Electronegativity in the structure of things like this is increasing electronegativity, going left to right and so forth like that, plays a big part in how structures hold bonds together. It's called bonding polarity. Okay, bond polarity uses electronegativity to make an unequal distribution of electronic charge around the 2 bonding nuclei. So if you have A and bond it to B, however you wish to look at it, and say B pulled all of the charge back over toward it because of a high electronegativity, whereas A might have a lower electronegativity, the attraction would be to build up all of the electronic charge around B. And this little symbol, arrow with a little cross on the back of it, is a symbol for a dipole. And as a result of this unequal distribution of charge that I'm trying to illustrate here, one end that was uncovering the nucleus, so to speak, would be, you draw a little S with a little tail on the end of it like that, and put a plus, a superscript. That means that's called a partial positive charge. And that's frequently used in a lot of literature. I'll draw this little symbol with a positive. It means a partial charge. It's not formal in terms of completely dominating a formal positive charge or negative charge. The other end with the excess of electrons, and this is a partial negative charge. Okay, what's the significance of that issue? Well, if something has a strong polarity, or one end of a molecule is positive and a bond is positive, the other end is negative, and something out here in you, whatever that animal is negative, you can expect it to start looking for the positive ends, and they'll hook up, maybe bond, and other things will change, and what have you. There's positives looking for negatives all the time. And so the electronegativity contributes to forming a polar distribution of electron density, and one end's positive, one end's negative. Now, carbon, for example, carbon, both of them have the same attraction for electrons, okay? And so what happens here is you don't have any unequal distribution. And if that's the case, no unequal electron distributions, say, hypothetically, this has a term, it's called non-polar covalent bond. Now, non-polar covalent bonds are very unreactive. In that there is no positive end and there's no negative end to be trying to attract something else floating by that has another opposite charge. Okay, here I'm going to take carbon with a certain electronegativity, and I'm going to bind it to carbon, and then I'm going to take carbon and nitrogen, carbon and an oxygen, carbon and a fluoride. Okay, so we're talking about bonds, okay? Now, this is electron pair in between each one, okay? Listen to me carefully, because this governs future work that you got to do. All of these are the same. So the change is carbon, nitrogen, oxygen, fluorine. So as I go down, you can tell from the periodic table, we have an increasing electronegativity going across the table, carbon, nitrogen, oxygen, fluorine. So we've got a strong electronegativity down here and a weak electronegativity up here. And what I want you to learn here is, how does that electronegative and charge distribution affect the strength of bond? How does it strength of bond? Well, why is that so important? Something that has a strong bond would have a weak reactivity or poor reactivity. Something with a very, very high electronegativity and a structure like you'll see in this, it would be very reactive. So poor distribution, low electronegativity has a strong bond. So we'll come up here and say this has the lowest electronegativity. So I'm going to put a little dotted line symmetrically distributed. So this has low electronegativity. And as a result, this is a very strong bond. And this has, as a result, poor reactivity. Poor reactivity on this end. You put in, it doesn't have any pluses or minuses, so it's not looking for anything. Okay? Now, as you go down, nitrogen is a little more electronegative than the carbon. So you'll find that nitrogen will have a little more buildup around it than carbon. So as a result, we will have a slight polarity. Some of the carbon has been uncovered a little bit. Okay? Well, nitrogen has a big buildup of charge and will be carrying a negative charge. And so if anything's floating by with a positive charge, it would be attracted to nitrogen and undergo reactivity, or something that's negative is floating around, it would probably attack the carbon because these are uncovered or overcovered with electrons. Now, the mechanisms on that are for the next level. What I want you to do is understand what the bond simply is doing in terms of, well, what's its role in this reactivity? Well, it's a dipole, and the positive ends are attracting negatives, and the negative ends attracting positives, so that leads to reactivity, which is the next level. So anyway, as we go down, we increase the electronegativity, so when we get to this oxygen-carbon bond, we'll see it significant growth in, and it's a very stronger dipole. And I put the little symbol in here for each of these. The longer the arrow, now let me get a little longer, stronger the dipole, if you will. And then when we get down here to carbon and fluoride, you see a large distribution around the fluoride and very small around the carbon. And this is a very large dipole. And so that carbon fluoride bond is very weak in here. Weak bond there, whereas that's a very strong bond. So weak bond gives you good reactivity. Okay, now the next thing is as far as we can go in reactions. Okay, but it's a rule that you want to keep in mind as you go to the next level. The natural path of reactivity is to form a stronger bond, always. So natural reactivity always forms a stronger bond. That's very important. So what you're going from is something that's highly electronegative, polarized, to something that is low polarity. For example, if I take this carbon fluoride right here, this is highly polarized, very reactive toward something that's, I'm going to NU negative, okay? It's a molecule. I don't know what it is. It's just, but it's got a big old nasty negative charge laying out there on the end of it somewhere, okay? A pair of electrons looking for something to bond to, okay? And this structure, this has a low electronegativity. Therefore, it donates a large amount of electron cloud. So something that is floating around has got a low electronegativity, and it's got a pair of electrons out there, could be a formable negative charge. We'll just put the negative up there. And this thing floats by something that is highly positive on one end, highly negative on the other end. This is going to be attracted to that carbon. And if it has a low electronegativity, it donates a large and ultimately forms a strong bond Now, the issue here is what happens. Here's your Nu negative. Here's the carbon bonded to the fluoride. And this is positive, and this is very negative here. So there's a lot of shift in charge there, and this is a weak bond. That's what's causing the bond to be weak. Now, this negative charge comes in here and hooks on to the carbon right there. This is a stronger bond than the carbon fluoride. This would make a stronger bond. Okay, this is weaker than the carbon nucleophile is what it's called. It's nuclear loving, positive loving. That's what it's called, nucleophile. I'll write it down here. And that's a big word in organic chemistry, nucleophile. That means nuclear loving. Nuclear, i.e. plus charge, loving. That's what the term means. So you got this nucleophile that's running around looking for positives, and so it sees this carbon fluoride sitting there. And so this nucleophile throws its electrons, or donates electrons very easily because of its inherent low electronegativity. And so the outcome is this nucleophile prefers to be hooked up to the carbon, and it loses the fluoride. It floats off into Never Never Land, out here at the end of it somewhere. And so that's the driving force of chemical bonding in molecular compounds. The tendency to form a stronger bond because of the attacking group is a low electronegativity, whereas the leaving group, the fluoride, has a high electronegativity. So you have low electronegative groups substituting and replacing high electronegative groups. So low electronegative groups, or whatever molecules, replace high electronegative groups. And so if we had something that had a low electronegative, that means it has a strong bond potential. And so here's this carbon, and hooked on to something with a high electronegativity, such as a fluoride, then this is going to want to bond to carbon more so than the fluoride, and that pair of electrons will take its fluoride and go, because the fluoride is pulling so hard on that bond pair between the carbon and the fluoride, it's going to suck them right off as soon as this, because it can't hold an extra pair of electrons. If you left that in there, you'd have well, you got another one hanging in there like that. You'd have 2, 4, 6, 8, 10, and you can't have that, so this will leave. The high electronegative element or group, and it comes in groups too, will group, and this is called the leaving group. High electronegative structures are leaving groups. Low electronegative or good attack groups. And that's how it's going to be presented to you when you go to the next level. Here's something floating around here that's negative, looking for a positive, and if that thing is attached to the positive, is more electronegative than what's floating around, it's going to replace it. It's going to leave. Okay? However, if that thing floating around is negative, like the fluoride is floating around, and you've already got a carbon nitrogen or carbon oxygen, it's not going to replace that, because the oxygen, nitrogen, and other carbons prefer to stay hooked up because they have a strong electron density in here. So another fluoride coming out wouldn't affect that. And that is the fundamental governing mechanics of how the chemical molecular dynamics works. It's positive looking for negatives, and all that positive negative hoopla that I'm making noise about is electronegativity. And then you just boil it down to that, and you pretty well master the subject pretty quickly in that context. All right, the next term that you have to take into account, and this is, we're talking about molecular polarity. That's an unequal distribution of charge around the entire molecule. We talked about this just briefly in terms of the bonds, non-polar covalent bonds. Well, now we'll talk about them in terms of non-polar covalent molecules versus polar covalent molecules. Okay, and we'll come down here and say polar covalent molecules. Okay, for non-polar covalent, something like methane, it has a symmetrical distribution, and I'm going to draw its three-dimensional geometry like this. It is a tetrahedral geometry, and you'll learn about that next time, how and what the base parent geometries are. We'll talk about this, but right now, just this is a symmetrical distribution of charge around this carbon right here. About the molecule. Okay, the result of this, so if you have an equal distribution around, what then happens? It is poor reactivity, in essence. It doesn't have any dipole moments in it. It doesn't have any positives and negatives in there. And all the bonds are extremely strong and they're not going to break down very easily. It doesn't ionize or come apart. However, if we start looking at a polar covalent molecule, we'll take one of these hydrogens off. Let's put a chloride on there. Okay, chlorine, and here's our carbon, and we'll make it look the same way. Carbon will bond tetrahedrally in that format. Well, here is a highly electronegative element. So what is that going to do? It's an electronegativity is an element's attraction for electron cloud. Well, there was nothing up here asymmetrical. Versus, well, this is symmetrical. Here is asymmetrical. I mean, uneven distribution, asymmetrical. That word's used thrown around a lot in organic chemistry. Versus symmetrical distribution of charge versus asymmetrical distribution of charge. Well, what happens is this chlorine-carbon bond is a strong dipole, and the arrow points to the negative end, and the plus end back here is a plus end. So this carbon has a strong positive charge. And so what is it looking for? Strong nucleophiles or reactive nucleophiles, Nu negative, such that when that nucleophile attacks that carbon, it forms a stronger bond than what the chlorine has with that carbon. If this nucleophile hooks up in here and that nucleophile is less electronegative than the chloride, low electronegative, then it's going to form a strong bond, and that chlorine is going to go off somewhere else. So this would be negative, attracting in here, and that would pull out electrons off because electronegative, and chlorine's gone. And so the outcome of this is, just to put it in perspective, this actually happens. Hydrogens flip over and kick out and so you have that nucleophile coming in here, throwing its electrons, and forms a stronger bond. Right there. And away goes the chloride with all its electrons, because its pair of electrons that it was using to bond didn't form as strong a bond as did the nucleophile coming in there. And so you made a new molecule. This is the natural tendency, and you know these things as you evaluate molecules. I say, yeah, that's a real polar thing. I'm going to give you something that's not polar, throw in there, and bam, you got a new molecule. Now, what that is the next level. Okay? What I want you to understand is the high electronegativity stuff, okay, is a weaker bond, and it's a good leaving group. Whereas low electronegativity form stronger bonds and are very reactive groups. Okay, we're going to start with kind of bond breaking. And just why I write it like that, I don't know. Okay, if you have a molecule, A bonded to B, like that, and for whatever process, you want to break those apart, breaking the bond in here. It breaks in one of two formats. It will break where one electron goes with A and one electron goes with B. This is called a homolytic cleavage. And these little elements with dots by them are free radicals. We're not going to study those in great detail, but I do want you to know what they are. Now you'll go on to some levels in some chemistries, and the professor doesn't know the difference between a free radical and an ionic cation anion. And they'll start calling anions and cations radicals. That's not true. In the strictest sense of the word, it is a structure or a polyion or a polystructure that has one electron and is not charged. Radicals don't carry charges. But anyway, that's about as far as I'm going to go with that. And I'll make this one a little bit further down here, gets more room. If this breaks, pair of electrons could go with one element, whereas the other element's left deficient, and you'll have an outcome like this. And this electron pair in here results in a negative charge. These are called formal charges. And they're thousands of times more reactive than are the partial positives and partial negatives I talked about a few minutes ago. In chemical reactions, the objective is to find something that will form a stronger bond. And when you have that, this is what happens. The one that will form the stronger bond, say a nucleophile, will have an electron pair. And here's, say, a carbon here with a leaving group right there. Okay, so this would come in here and hook up to that carbon, and this electron pair would shift off and you just split away. And when it does, see how you get both electrons going out. The leaving group will go off and have that negative charge, and you will have cleaved this one such that you are forming a leaving group that's negative. This one came in with an electron pair, and this is a stronger bond right here, and this is a weaker bond. And there are whole bunches of leaving groups, highly electronegative. If you understand that, you're a leg up, a mile ahead of everybody else in the organic class. You know how to pick out the electronegative group. Matter of fact, in a chemical structure, or chemical structures in general, are either neutral structures or charged particles. And these are polyions. Okay, or you can have neutral particles. And those are, say, your covalent molecules. regardless of whether it's a polyion or whether it's a neutral covalent molecule, each element within a structure has what is called a formal charge. Each element. And the sum of formal charges equals the net molecular charge. Okay? So you can pick out an individual element and calculate its formal charge, and you pick out another element and do its formal charge. You go through all the elements in the structure, and then you add them up algebraically. And if that's a polyion, it'll leave you with a positive or negative 1, 2, whatever, like that. Okay, so let's nitrite. Okay, to calculate the formal charge, we disregard the complex structure. So our interest is the formal charge on nitrogen, formal charge on this oxygen, formal charge on this oxygen, and the net overall charge, if it has a net charge. Okay, formal charge is given by the formula valence number of the element, what are the number of valence electrons, minus total number of bonded electrons, not bonded pairs, but total electrons. If you got a bond, it means 2. Okay, divided by 2 minus n, non-bonded electrons. So V is valence electrons. B is equal to total electrons bonded. And N is the total non-bonded electrons. Right there. Okay, now I'll have to redraw this real quick for you. You can draw a circle and okay, so you're given a molecule on the exam and asked to calculate the formal charge on nitrogen. Okay? At nitrogen. Okay? All right. So what's the valence of nitrogen? 5. Okay? So valence of nitrogen is equal to 5. Okay. The total number of bonded electrons. Well, each bar represents 2 electrons. Okay, so bonded electrons about nitrogen. I've got 1, 2, 3, 4. Well, it's got 8. Okay, so that's 8 electrons total. 4 bonds times 2. Non-bonded electrons for the nitrogen is 0. You don't have any of these free pairs out here. Closer together right there. You don't have any free pairs, so you put a 0. So your formal charge at nitrogen is your valence minus bonded over 2 minus non-bonded. Valence is 5 minus 8 over 2. I'm about to write the 4, but 8 over 2 minus 0. That's 5 minus 4, and that's a plus 1. So we'll have a plus right there. Okay? Now, let's do the top oxygen. The double bonded oxygen, formal charge, and I'll just put that in there. The valence on oxygen is 6. Okay, it's got 4 bonded electrons in here, 4 over 2, and it's got 4 non-bonded electrons, which is 6 minus 2 minus 4, and overall that's a minus 2. So I'm going to put a minus 2 right there on that element. Make sure I've got it. Valence 2, 4 total. 2, 1, 2, 3, 4, and then we have 4 non-bonded electrons, and so 2 into 4 is 2, minus 4, 4. Now that's 0, isn't it? I'm sorry. Getting ahead of myself here. 0, sorry about that. So that doesn't have a charge either, right there. It only has a +1 right there. Now we get the formal charge on the single bonded oxygen. Right there, it's 6 minus 2 over 2 minus 6. And so 6 minus 6 is 0, so we have a -1 for that one. So this carries a -1. All right, the sum of all your charges in here, this is 0, -1, +1. So this entire molecule is neutral. That's the way that little show is written. Okay, I'm running out of time, so I'm going to push this a little bit. Let's do SO4, 2 minus. And here is SO4. Well, is it neutral or does it carry a charge? Well, it's a polyion that we've played with before, and you should expect a -2 out of it, like that. So we'll start with the oxygens. When you got to calculate one of the oxygens, I got all 4 of them, right? So formal charge of the oxygens right here is valence minus bonded number over 2 minus non-bonded. 6 for the valence minus, well, we got 2 on each one, so 2 over 2 minus 6, and so each oxygen's carrying a -1. So I have a minus here, got a minus right there, got a minus right there, minus there. So each one of them carrying a minus charge. Now the formal charge on the sulfur in the middle is done the same way. So the valence of sulfur is 6, and you got 2, 4, 6, 8 bonded pairs, or 4 bonded pairs and 8 total electrons, that is. And it doesn't have any non-bonded pairs, so we put a 0 in there. It doesn't carry any non-bonded pair. So that's 8 over 2 is 4. 6 minus 4 is a +2. So right here is a +2 formal charge on that structure. So when I add up the sum of all your charges, your net charge, okay, so I have 4 times -1 plus 1 times a +2, and this overall is a -2 net. So your sulfate -2 net. So you can figure out each one, and that's where the charges come from on these polyions. And how do you figure them? On test day, I'll give you a molecule drawn out and simply ask you to, well, what's the net charge on this molecule? You know, +1, 2, 3, 4, whatever, like that. Okay. Resonance structures are structures which have more than one Lewis dot structure. I'm just going to say multiple, 2 or more. One is very simple, and this is sulfur dioxide. Now, it can be drawn as this. Like that, or it can be drawn like this with the double bond on the right side. And the general response to this is, oh, well, you just turn it around. Well, that's not the issue. This is a resonance structure in here, in that neither one of these drawings is the true structure. The true structure is what we call a resonance hybrid of the two. It's like blending them together. Like I say, there's a lot of terminology and stuff like that. And what is actually happening is you have one of the double bond is actually distributing itself, and this is, you put dots like this, like that, and this is a resonating electron cloud in the structure. Now, the only thing I'm going to hold you responsible for is that definition, and maybe draw out something simple like this. Does this have a resonance structure? Alternating single double bonds are resonance structures. Have a double single or double single. That means they can resonate back and forth. If they're split, like this, that's not going to be a resonance structure, but with this down here. It can either be here or there. Okay, there's one classic molecule, and I'll be through this one time, is benzene. Benzene is a resonance molecule, and many of you have seen this in your bio courses and so forth, and I think it's worth mentioning. Benzene is a cyclohexadiene in general. A triene, not diene, triene. And what that means is it's carbon, 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 and carbon. And it has alternating single double bonds. Like this, and each of the carbons has a hydrogen on it. And this is one resonance structure. And the other resonance structure on this, we can draw carbon, 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 and see up here is where the double bond is. Well, we can shift that over one like this, and this would be the other resonance structure. And this is a resonance hybrid and called Kekulé structures, K-E-K-U-L-E structures. Now, the true structure is a resonance structure between the carbons. In which one of the electron clouds we'll learn more about distributes itself throughout the entire molecule. And what is done, for the most part, when you have a ring structure like this, or a resonance structure, you write that as a bar or stick structure and put a ring in the middle of it. And this represents the resonance structure, and these little points right here are all carbons right here. I'm just about through. And you assume the hydrogen presence. And you see these many places throughout your science studies, in which people will draw structures like this, not that it's like this, and you'll see a resonance structure hanging on the end with a little ring in it, and that has a lot to do with the reactivity of the molecule. And so when the time comes, you'll learn how to identify the most reactive sites in that resonance structure. But right now, all you need to understand is this structure has, well, one of them's covalent all the way around, one of them's distributed. So the last little diagram here, and in reality it has a halo of electronic charge above it and a halo of electronic charge below it. And so that's your benzene resonance.